Now let us start with the topic chemical kinetics. The meaning of this word kinetics is similar to that of a speed. In this topic, we are going to study the speed of chemical reactions. Before going in a detail about this topic, let me give you one simple example to understand this topic. Suppose a vehicle is running on a road and you are asked to determine the average speed of that vehicle. Then you need two values. One is the distance traveled by that vehicle from starting point up to the end point at which that vehicle stops, and the time taken by that vehicle to travel that much distance. By using these two values, you can easily calculate the average speed of that vehicle. Similarly, to calculate the speed of a chemical reaction, that is nothing but the rate of a reaction, you need these two values. That is the change in concentration of a reactant with respect to time, or change in concentration of a product with respect to time. The negative sign in front of this quantity indicates that with the time the concentration of a reactant goes on decreases, and the positive sign in front of this quantity dCp upon dt indicates that with the time concentration of a product increases. Now to understand this equation, let us consider a general reaction. Reactant A when we mix with a reactant B, then there starts a reaction between these two reactants. When there starts a reaction between these two reactants, the concentration of a reactant, it goes on decreases along this first curve. At the same time, the concentration of a product goes on increases along this second curve. Any point on this first curve represents the change in concentration of a reactant after a definite time interval from the initiation of a reaction. Similarly, any point on this second curve represents the change in concentration of a product after a definite time interval from the initiation of a reaction. So by determining this change in concentration of a reactant per unit time, or change in concentration of a product per unit time, it is possible to calculate the rate of a reaction. Thus, rate of a reaction is defined as it is the change in concentration of a reactant per unit time, or change in concentration of a product per unit time. Now then, in this topic, we are going to study about the factors affecting the rate of a reaction. Increases. The scientist Arrhenius, he has given the correlationship between the rate constant of a reaction and the temperature of a reaction mixture. If you carefully look at this Arrhenius equation, so you will come to know that the rate constant K of a reaction is directly proportional to this temperature. So as temperature of a reaction mixture increases, the rate constant K also increases. Further, the rate constant K is inversely proportional to the energy of activation. This means that lower is the energy of activation for the given reaction, higher will be the rate constant. So what this energy of activation is? Energy of activation, that is nothing but it is the minimum amount of energy that is required for the reactant molecules to react with each other upon collision, is known as the energy of activation. Now then, the second factor on which the rate of a reaction depends upon is the concentration. It is found that as the concentration of a reactant in the reaction mixture increases, with that the rate of a reaction also increases. The next factor is the nature of a reactants. The rate of a reaction depends upon the nature of a reactant. Nature of a reactant, that is nothing but whether these reactants are there in a gaseous state or in the form of a ions. When the reactants are there in the form of a gaseous state, then these reactants reacts very slowly. On the other hand, when the reactants are there in the form of ions, and that too, if both the ions are oppositely charged ion, then the reaction between the oppositely charged ion proceeds very fast. The rate constant of ionic reaction is very fast, is very high as compared to the rate constant of a reaction between the gaseous reactant molecules. The another factor on which the rate of a reaction depends upon is the presence of a catalyst. You know that catalyst is that substance which alter the rate of a reaction, or we can say further that which can increase the rate of a reaction. When the reaction is carried out in the presence of catalyst, then that reaction proceeds with a faster rate than when the same reaction is carried out in the absence of catalyst. So like this, the rate of a reaction depends on these many factors. Now then, the classification of reactions. We can classify the reactions on the basis of order of reaction, molecularity of a reaction, and then the rate of a reaction. Now let us see how the reactions are classified on the basis of order of reaction. The number of atoms or molecules whose concentration determines the rate of a reaction is known as the order of reaction. When the rate of a reaction is independent upon the concentration of a reactant, then we call that reaction as a zero order reaction. Uh, Suppose the reaction is there between the hydrogen gas and oxygen gas. This reaction proceeds so slow that it takes several months to go for a completion, because the rate of this reaction is independent upon the pressure of a hydrogen gas and the pressure of a oxygen gas. This is one of the example of a zero order reaction. Now then, whenever the rate of a reaction depends upon the first power of a concentration of a reactant, then we call that reaction as a first order reaction. For example, suppose the reaction, uh, for example, suppose A giving rise to product. A is only one reactant which is involved in the reaction giving rise to a product of B. The rate of this reaction depends upon the first power of a concentration of a reactant A only. That's why we call this reaction as a first order reaction. Then the second order reaction. Whenever the rate of a reaction depends upon the concentration of a two reactants, then we call that reaction as a second order reaction. Suppose the reaction mixture consisting of reactant A and reactant B. These two reactants reacts with each other to give us a product of B. The rate of this reaction depends upon the first power of a concentration of a reactant A and the first power of a concentration of a reactant B. So therefore, the order of reaction N becomes equal to 1 plus 1, that is 2. The reaction is second order reaction. So likewise, we can define this term third order reaction also. Now then, the molecularity of a reaction. The number of molecules taken part in the step leading to the formation of a product is known as a molecularity of a reaction. On the basis of number of molecules taken part in the reaction, we can classify the reactions as a unimolecular reaction, bimolecular reaction, termolecular reaction, etc. Whenever only one reactant molecule has taken part in the step in which the product is formed, then we call that reaction as a unimolecular reaction. For example, say A giving rise to product. In this reaction, only one reactant molecule A has taken part. So therefore, we call this reaction as a unimolecular reaction. Then bimolecular reaction. Whenever two reactant molecules, say A and B, taken part in the step in which the product is formed, then we call that reaction as a bimolecular reaction. So likewise, we can define the term termolecular reaction also. Now then, the reactions are also classified on the basis of rate of a reaction as a slow reaction, moderately fast reaction, and ultra fast reaction. Uh, Whenever the reaction proceeds very slowly, for example, say the reaction between hydrogen gas and oxygen gas, this reaction is this reaction proceeds so slow that it takes several months to go for a completion. uh, it is very difficult to determine the rate of this reaction in a laboratory. This is one extreme. At the other extreme, there are certain ionic reaction. They proceed so fast that within few microseconds they go for a completion. For example, say the ionic reaction. For example, say the reaction between silver nitrate and sodium chloride. This reaction is one of the fastest reaction. This is the other extreme. In between these two extremes, there are certain reactions which proceeds with a measurable rate. We call them as a moderately fast reactions. And in a laboratory, we can determine the rate of these moderately fast reactions. For example, say the acid catalyzed hydrolysis of methyl acetate reaction. This reaction proceeds with a measurable rate. And we can determine the rate of this reaction in a laboratory by using the classical method. To determine the rate constant or a rate of a fast reactions and ultra fast reactions, some modern techniques are in use. They are stopped flow technique and flash photolysis. These techniques are used to study the kinetics of such a fast and ultra fast reactions. Now then, two important theories have been developed to explain the rate of a reaction. In that, the first one is the collision theory and second one is the activated complex theory. We are going to study in a detail both these theories in the latter part of this topic. Let us discuss in a detail about the collision theory. Collision theory attempts to explain the reaction rates on the basis of collision between the reactant molecules. To understand this, consider with us a large container is there and this container is confined with a gas. The molecules present in that gas, they are in a state of continuous motion because of having a very weak cohesive force between them. These moving molecules, they collide on one another. This intermolecular collision leads to the chemical reaction. This collision theory is applicable only to the gaseous state reactions and to some liquid state reactions. This collision theory is based on some assumptions. In that, the first assumption is that the reactant molecules have a rigid spherical shape which describe only the translational motion. The second assumption is that the reactant molecules, they must collide on one another for a reaction to take place. During the collision, an exchange of energy takes place between the reactant molecule in such a manner that there is no net loss or gain of energy. This means that the energy of the system remain constant. Such a collisions are called elastic collisions. The next assumption of this theory is that during the collision, some molecule acquire the activation energy necessary for the reaction to take place. Such a collisions are called effective collision. To understand this, let us take this simple example. In a container, whatever the total number of gas molecules are there, the kinetic energy of all the gas molecules is not same. Some gas molecules, they are having a very low kinetic energy, and some of the gas molecules, they are having very high kinetic energy. But large number of such a gas molecules are there, they are having the considerable amount of energy. The molecules which are having low kinetic energy, they acquire the kinetic energy due to the series of collision in one right direction. So like this, the kinetic energy of a gas molecules in that gaseous mixture, it increases. When the gas molecules acquire the activation energy, and after then when they go for a collision, then that collision will be the effective collision, and the effective collision leads to the formation of a product. The next assumption is that for effective collision to take place, the molecule must be properly oriented before collision. Look at this example. This molecule C is moving diagonally, whereas this molecule D is moving horizontally from left to right. These two moving molecules, they just touches one another. The collision between these two molecules will not be the head-on collision like these two molecules. So therefore, this type of a collision with a poor orientation simply increase the kinetic energy of one of the reactant molecule. This type of a collision does not leads to the formation of a product. Now the next assumption is when a molecule take part in a effective collision, a rearrangement of a bond takes place and the product is formed, and the next assumption is that the rate of a reaction is directly proportional to the total number of collisions taking place between the reactant molecules in a per unit time, per unit value. So like this, we need to explain about the assumptions of collision theory of reaction rates. Now this collision theory can be applied to study the rates of a bimolecular reaction, as we already have discussed about the molecularity of a reaction. Whenever two reactant molecules, say A and B, takes part in the step leading to the formation of a product, then we call that reaction as a bimolecular reaction. Uh, the rate of this bimolecular reaction can be determined by taking into account the relation between the number of collisions Z and the rate constant of the reaction, that is K, and also the number of effective collisions. According to the kinetic theory of gases, the number of collisions taking place between the like molecules is given by an equation. Z11 is equal to 2n square sigma square root of pi kt upon m. In this equation, this Z11, that is nothing but the number of collisions taking place between the two A molecule or like molecules, N square denotes the total number of molecules present in that container, and sigma denotes the collision diameter. Collision diameter, that is nothing but the closest distance of approach between the two collided molecules, and m is the molecular weight of reactant molecule. The number of collisions taking place between different molecules, that is nothing but, suppose in the reaction mixture two types of molecules are there. One is type A molecules, another one is type B molecules. Then the number of collisions taking place between them can be calculated by using this equation Z12. This one is for capital A, this 2 is for say capital B. Z12 is equal to N1N2. N1, that is nothing but number of molecules of a first type, say A. N2, that is nothing but number of molecules of a second type, say B. And sigma square is the average collision diameter. This average collision diameter can be calculated by taking the mean of the collision diameter of the molecules. Pi is the constant, K is the Boltzmann constant, and the Boltzmann constant K is equal to R upon N, where R is the gas constant and N is the Avogadro's number. T is the temperature in Kelvin. M1 is the molecular weight of molecules of a first type. M2 is the molecular weight of a second type. So like this, by using this equation, we can calculate the number of collisions taking place between the different molecules in per second per cubic centimeter volume. For the dissociation of a hydrogen iodide, say 2HI gas giving rise to H2 gas plus I2 gas. For this particular gaseous state reaction, the value of a Z is found to be equal to 6 into 10 to the power 31 collisions per second per cubic centimeter, whereas the value of a rate constant K is found to be 2.108 into 10 to the power 14 mole per second per cubic centimeter. If you carefully think over this, you will come to know that here there is a large difference between these two molecules. The number of molecules actually colliding is 10 to the power 31. This number is very large number, but the number of molecules actually reacting is just 10 to the power 14. This large difference is mainly due to the two following reasons. Those reasons are: the molecules may not have acquired the activation energy before going for a collision. This may be the first reason for this large difference. And the second reason is that the molecules may not be oriented properly before collision. Because of these reasons, we found this difference between the number of molecules colliding and the number of molecules actually reacting with each other. The specific reaction rate constant K for such a gaseous state bimolecular reaction can be calculated by using the equation, that is K is equal to Z into the Boltzmann constant. This equation is called as the fundamental equation of the collision theory for bimolecular reaction. However, for many reactions, the calculated value of a K is found to be much greater than the experimentally observed value of a K. Hence, to minimize this difference, the above equation is modified as K is equal to P into Z into the Boltzmann constant. This factor P is called the probability factor. This factor P is introduced to minimize the difference between the calculated value of a K and experimentally observed value of a K. The value of this probability factor P ranges from 1 to 10 to the power minus 9. When the value of a probability factor P is found to be equal to 1, then that particular gaseous state reaction obeys the collision theory. Now let us study the collision theory for unimolecular reaction. It is very difficult to apply the collision theory to study the rate of a unimolecular reaction, because according to the collision theory, for the collision to take place, at least two reactant molecules are required. This difficulty was solved by the scientist Lindemann, and he applied the collision theory to study the rates of a unimolecular reaction. According to Lindemann's theory, the reactant molecules get activated during the collision. The activated molecule decomposes to give the product. Further, there exists a time lag between activation and decomposition. When this time lag is large, this means that when this activated molecule remain in a activated state for a long period of time, then this activated molecule collides with a normal molecule and gets deactivated back into the normal reactant molecules. When the rate of deactivation is greater than the rate of decomposition, the reaction will be unimolecular reaction. Further, the rate of such a reaction will be proportional only to those activated molecules which retain the activation energy and decomposes to give the product. Now consider a unimolecular reaction, A giving rise to product. The reaction takes place in two stages. The first stage of this reaction, the reactant gas molecule present in the reaction mixture collides on one another, say with a rate constant K1. Out of these two molecules, one molecule gets activated. This means that the energy of this molecule increases or is greater than the ordinary molecule. This activated molecule, because of having large energy, is unstable, and in order to attain the stability, this activated molecule with a rate constant K3 decomposes to give the product. Further, the rate of formation of activated molecule is given by this equation, is equal to K1 concentration of A bracket square, because here there are two reactant molecules, that's why here there is a square. Then the rate of disappearance of the activated molecule. See here, the formed activated molecule gets disappeared in the reverse reaction in the first stage and in the forward reaction of a second stage. So K2, rate constant K2, the rate of disappearance of this activated molecule depends upon its own concentration and the concentration of A. So therefore K2 concentration of A into concentration of A star plus K3 concentration of A star. According to steady state principle, the rate of formation of a activated molecule A star is equal to the rate of disappearance of the activated molecule. So rate of formation of an activated molecule is given by K1 concentration of A square, and rate of disappearance of an activated molecule is given by this equation. We had taken it as it is. So we can simplify this equation. We can take this concentration of an activated molecule as a common, and we can rewrite the remaining equation in a bracket, that is K2 concentration of A plus K3, or concentration of an activated molecule is equal to K1 concentration of A bracket square divided by K2A plus K3. So like this we can write the equation for the concentration of activated molecule. Since the rate of a reaction is proportional to the concentration of a activated molecule, the rate of a reaction is given by an equation. So minus D concentration of A upon dt is equal to K3 concentration of A star. Let us substitute the value of a concentration of a activated molecule in this equation. We will get this equation number 1. In this equation, in the denominator of this equation, only two quantities are there. One is K2A and another one is K3. Hence this equation has got only two particular cases. Let us see one by one. Case first. When K3 is smaller than K2A, this means that when the rate of decomposition is less than the rate of deactivation, under this condition, the denominator of the above equation number 1 becomes K2A plus K3 is approximately equal to K2A. Let us substitute this condition in this equation number 1, so we will get this equation. In this equation, we can cancel out 1a from a numerator and 1a from a denominator, and in place of this ratio of a rate constant we can write K dash. So if you look at this equation, you will come to know that the rate of a reaction is directly proportional to the first power of a concentration of only one reactant A. This means that this reaction follows the first order kinetics. Secondly, as if only one reactant molecule is involved in the reaction step leading to the formation of a product, the reaction becomes unimolecular reaction. Let us think of case second. When K3 is greater than K2A, this means that when the rate of decomposition is greater than the rate of deactivation. Under this condition, the denominator of equation number 1 becomes K2A plus K3 is approximately equal to K3. Let us substitute this condition in this equation number 1, so we will get this equation. We can cancel out K3 and K3 from numerator and denominator, and we will get this final equation. If you look at this equation, so you will come to know that the rate of reaction is directly proportional to the second power of concentration of reactant A. This means that this reaction follows the second order kinetics, and this reaction is a bimolecular reaction, because in the step that leads to the formation of a product, two reactant molecules have taken part. So therefore, the molecularity of this reaction is 2. Then what are the merits or advantages of collision theory? Collision theory explains the effect of temperature on the rate of a reaction. We know that with increase in a temperature, the thermal energy of a gaseous molecule increases, and due to that their kinetic energy increases. As the kinetic energy increases, the number of collisions between the reactant molecule increases, and due to the increase in the number of collisions, the rate of a reaction increases. So like this, the collision theory explains the effect of temperature on the rate of a reactions. The second merit of this collision theory is that this theory is very simple to apply for the reactions taking place in a gaseous state. The third merit of this theory is that the calculated and experimentally obtained value of a rate constant for a simple bimolecular gaseous reaction match with each other. And the next merit of this theory is that it provides easy calculations for the rate constant of the reaction. So these are the merits of collision theory of reaction rate. Now then, what are the drawbacks or failures of collision theory of reaction rates? The first drawback of a collision theory of a reaction rate is that this theory is applicable only to the gaseous state reactions. Then this theory fails to explain the complex gas phase reactions. This theory cannot be applied for very slow or very fast reactions. The next drawback is that for many reactions, theoretically calculated value of a Z and the Boltzmann constant differ considerably from the experimentally obtained values. The next drawback is that to explain the unimolecular reactions, different assumptions are required. This is again one of the drawback or limitation of this collision theory of reaction rates. This collision theory fails to account for the vibrational and rotational energy changes taking place during the complex reactions. The collision theory has taken into account only the translational motion but not the vibrational and rotational energy changes they are taking place during the complex reactions. The next drawback of this collision theory is that the atomic and molecular structures changes considerably because of the quantum mechanical treatment. Thus, it is unconvincing to picture a molecule as a rigid sphere. The next drawback is that different rates are obtained for the same reaction. Collision theory fails to account for the different rates. And the last drawback of this collision theory is that in a chemical reaction where we consider the transfer of electrons between the reacting molecules, the idea that the molecules should have sufficient activation energy will be unconvincing. So these are the drawbacks or the failures of collision theory of reaction rates. Now let us study about the fast reactions. As we had seen in the introductory part of this topic, the reactions are classified on the basis of their rate constants also. The classification of a reaction on the basis of their rate constant and half time is given in the table below. We call that reaction as a slow reaction of which the rate constant K is 10 to the power minus 7 decicubic meter per mole per second, or the half time is 10 to the power 8 seconds, that is nothing but about 3 years. The well-known example of such a slow reaction is this gaseous reaction, that is the reaction between hydrogen gas and oxygen gas to give us the liquid water. Then the moderate reactions or moderately fast reactions are those reactions of which the rate constant K value is between 10 to the power minus 4 to 10 to the power minus 1 decicubic meter per mole per seconds, or the half time is 10 to the power 5 to 10 to the power 2 seconds. Now then, the fast reactions are those reactions of which the rate constant K value is 10 to the power 2 to 10 to the power 5 decicubic meter per mole per seconds, or the half time is 10 to the power minus 1 to 10 to the power minus 4 seconds. Now there are some ultra fast reactions are there. The rate constant K value of such a ultra fast reaction is about 10 to the power 11 decicubic meter per mole per seconds, and their half time is very short, that is 10 to the power minus 12 to 10 to the power minus 15 seconds. So like this, we can classify the reactions on the basis of the rate constant K value and the half time. Example of one of the fastest reaction is the reaction between H plus and OH minus ion to give a H2O molecule. See here, the rate of such a fast reaction can be determined by using Stoff flow method. Now let us try to understand what this Stoff flow method is and how it is used to determine the rate of a fast and ultra fast reactions. This is the instrumental setup of a Stoff flow method. In this setup, these two are the syringes which are filled with solutions or a reactant. Then this is the mixing chamber. This is the mixing chamber where the two reactant solutions they get mixed together within 10 to the power minus 3 seconds. And then this unit is the reaction cell through which the beam of a monochromatic light passes, and this is the outlet of this stopped flow instrumentation. Now how this stopped flow technique is used to determine the rate of a fast or a ultra fast reaction. So let us see that. In this method, the reactant solutions are forced through the syringe jet into a mixing chamber. The reactant solution is forced through the syringes, forced through the syringe jet into the mixing chamber. The mixing chamber is so designed that mixing occurs in 10 to the power minus 3 seconds. The reaction mixture is then passed into the reaction cell. When the reaction cell is sufficiently filled with the reaction mixture, then the flow is stopped suddenly and the concentration of a reactant or product is determined as a function of time using spectrophotometric technique. Now then, what are the advantages of this stopped flow technique? One of the most important advantage of this stopped flow technique is that very small amount of reactant solution is required to determine the rate of a reaction. The second advantage is that this method is not affected by the rate of flow of reactant solution, provided the mixing is proper. The next advantage is that the transient intermediates, that is nothing but the short-lived intermediates, can be detected and their concentration can be measured by using this technique. And the last advantage of this technique is that a permanent record for the progress of a reaction can be obtained in the form of a spectrum of absorbance versus time. So like this stopped flow technique can be used to determine the rate of fast and ultra fast reactions. Now then, the next technique used is the flash photolysis technique. This flash photolysis technique is discovered by Norrish and Porter to study the kinetics of those fast reactions which are induced by the absorption of light radiations. Now, what's the principle underlying this flash photolysis technique? The reactant system is irradiated with an intense flash of ultraviolet or visible radiation for a very short duration so as to produce a measurable change in concentration. The subsequent chemical changes are then recorded by flash spectroscopy or kinetic spectrometry. The instrumentation required for this technique is shown in the figure below. This instrumentation, it consists of this thermostated a container, sample container. Then this is a monochromator so as to produce a beam of a required wavelength. Then this is photoelectric detector to convert the light radiations into the electrical signals. Then this is the oscilloscope, and then this is a flash lamp and voltage supply and trigger signals. See, these are the components of the flash photolysis instrumentation. This flash photolysis instrument consists of three parts, important parts. The first part is the flash of a high intensity with the energy of 2 joule to 2000 joule is produced for a time interval of 1 to 100 microseconds. How? By charging or discharging of a series of voltage condenser. Then the reaction vessel with a suitable thermostatic arrangement. This is the reaction vessel with a suitable thermostatic arrangement. Then a suitable arrangement is made for monitoring the change in absorbance. That is monochromator, photoelectric detector, oscilloscope to record the absorbance versus time plot. Now then, how this flash photolysis instrument works? The reaction mixture is placed in a reaction vessel. This reaction mixture is then irradiated with a flash of UV or visible radiation for few microseconds. The subsequent chemical changes are then recorded by measuring the absorbance as a function of time. The rate constant is then determined by using the absorbance versus time spectra.